In physical cosmology, cosmic inflation, cosmological inflation, or just inflation is a theory of exponential expansion of space in the early universe. The inflationary epoch lasted from 10-36 seconds after the Big Bang to sometime between 10-33 and 10-32 seconds. Following the inflationary period, the universe continues to expand, but at a less rapid rate. Inflation theory was developed in the early 1980s. It explains the origin of the large-scale structure of the cosmos. Many physicists also believe that inflation explains why the universe appears to be the same in all directions, why the cosmic microwave background radiation is distributed evenly, why the universe is flat, and why no magnetic monopoles have been observed. While the detailed particle physics mechanism responsible for inflation is not known, the basic picture makes a number of predictions that have been confirmed by observation. The hypothetical field thought to be responsible for inflation is called the inflaton. In 2002, 3 of the original architects of the theory were recognized for their major contributions: physicists Alan Guth of MIT, Andre Lind of Stanford and Paul Steinhardt of Princeton shared the prestigious Dirac Prize for development of the concept of inflation in cosmology. Overview: an expanding universe generally has a cosmological horizon, which, by analogy with the more familiar horizon caused by the curvature of the Earth's surface, marks the boundary of the part of the universe that an observer can see. Light emitted by objects beyond the cosmological horizon never reaches the observer, because the space in between the observer and the object is expanding too rapidly. The observable universe is one causal patch of a much larger unobservable universe. Other parts of the universe cannot communicate with Earth yet. These parts of the universe are outside our current cosmological horizon. In the standard hot Big Bang model, without an inflation, the cosmological horizon moves out, bringing new regions into view. Yet as a local observer sees such a region for the first time, it looks no different from any other region of space the local observer has already seen. Its background radiation is at nearly the same temperature as the background radiation of other regions, and its space-time curvature is evolving lockstep with the others. This presents a mystery. How did these new regions know what temperature and curvature they were supposed to have? They couldn't have learned it by getting signals, because they were not previously in communication with our past light cone. Inflation answers this question by postulating that all the regions come from an earlier era with a big vacuum energy, or cosmological constant. A space with a cosmological constant is qualitatively different. Instead of moving outward, the cosmological horizon stays put. For any one observer, the distance to the cosmological horizon is constant. With exponentially expanding space, 2 nearby observers are separated very quickly, so much so that the distance between them quickly exceeds the limits of communications. The spatial slices are expanding very fast to cover huge volumes. Things are constantly moving beyond the cosmological horizon, which is a fixed distance away, and everything becomes homogeneous. As the inflationary field slowly relaxes to the vacuum, the cosmological constant goes to zero and space begins to expand normally. The new regions that come into view during the normal expansion phase are exactly the same regions that were pushed out of the horizon during inflation, and so they are at nearly the same temperature and curvature, because they come from the same originally small patch of space. The theory of inflation thus explains why the temperatures and curvatures of different regions are so nearly equal. It also predicts that the total curvature of a space slice at constant global time is zero. This prediction implies that the total ordinary matter, dark matter and residual vacuum energy in the universe have to add up to the critical density, and the evidence supports this. More strikingly, inflation allows physicists to calculate the minute differences in temperature of different regions from quantum fluctuations during the inflationary era, and many of these quantitative predictions have been confirmed. Space expands. To say that space expands exponentially means that two inertial observers are moving farther apart with accelerating velocity. In stationary coordinates for one observer, a patch of an inflating universe has the following polar metric. This is just like an inside-out black hole metric. It has a zero in the component on a fixed radius sphere called the cosmological horizon. Objects are drawn away from the observer towards the cosmological horizon, which they cross in a finite proper time. Since the space-time metric has no explicit time dependence, once an observer has crossed the cosmological horizon, observers closer in take its place. This process of falling outward and replacement points closer in are always steadily replacing points further out, an exponential expansion of space-time. This steady-state exponentially expanding space-time is called a de Sitter space, and to sustain it there must be a cosmological constant, a vacuum energy proportional to everywhere. In this case, the equation of state is: the physical conditions from one moment to the next are stable. The rate of expansion, called the Hubble parameter, is nearly constant, and the scale factor of the universe is proportional to. Inflation is often called a period of accelerated expansion because the distance between two fixed observers is increasing exponentially, while can stay approximately constant. This pushes the universe into a very simple state, in which it is completely dominated by the inflaton field, the source of the cosmological constant, and the only significant and homogeneities are the tiny quantum fluctuations in the inflaton. If the universe was only hot enough to form such particles before a period of inflation, they would not be observed in nature, as they would be so rare that it is quite likely that there are none in the observable universe. Together, these effects are called the inflationary no-hair theorem, by analogy with the no-hair theorem for black holes. The no-hair theorem works essentially because the cosmological horizon is no different from a black hole horizon, except for philosophical disagreements about what is on the other side. The interpretation of the no-hair theorem is that the universe expands by an enormous factor during inflation. In an expanding universe, energy densities generally fall, or get diluted, as the volume of the universe increases. For example, the density of ordinary, cold, matter goes down as the inverse of the volume. When linear dimensions double, the energy density goes down by a factor of 8. The radiation energy density goes down even more rapidly as the universe expands, since the wavelength of each photon is stretched, in addition to the photons being dispersed by the expansion. When linear dimensions are doubled, the energy density in radiation falls by a factor of 16. During inflation, the energy density in the inflaton field is roughly constant. However, the energy density in everything else, including inhomogeneities, curvature, anisotropies, exotic particles, and standard model particles is falling, and through sufficient inflation these all become negligible. This leaves the universe flat and symmetric, and mostly empty, at the moment inflation ends and reheating begins. Duration. A key requirement is that inflation must continue long enough to produce the present observable universe from a single, small inflationary Hubble volume. This is necessary to ensure that the universe appears flat, homogeneous and isotropic at the largest observable scales. This requirement is generally thought to be satisfied if the universe expanded by a factor of at least 10^26 during inflation. Reheating. Inflation is a period of supercooled expansion, when the temperature drops by a factor of 100,000 or so. This relatively low temperature is maintained during the inflationary phase. When inflation ends, the temperature returns to the pre-inflationary temperature. This is called reheating or thermalization because the large potential energy of the inflaton field decays into particles and fills the universe with standard model particles, including electromagnetic radiation, starting the radiation-dominated phase of the universe. Because the nature of the inflation is not known, this process is still poorly understood, although it is believed to take place through a parametric resonance. Motivations. Inflation resolves several problems in Big Bang cosmology that were discovered in the 1970s. Inflation was first proposed by Guth while investigating the problem of why no magnetic monopoles are seen today. He found that a positive energy, false vacuum would, according to general relativity, generate an exponential expansion of space. It was very quickly realized that such an expansion would resolve many other long-standing problems. These problems arise from the observation that to look like it does today, the universe would have to have started from very finely tuned, or special, initial conditions at the Big Bang. Inflation attempts to resolve these problems by providing a dynamical mechanism that drives the universe to this special state, thus making a universe like ours much more likely in the context of the Big Bang theory. Horizon problem. The horizon problem is the problem of determining why the universe appears statistically homogeneous and isotropic in accordance with the cosmological principle. For example, molecules in a canister of gas are distributed homogeneously and isotropically because they are in thermal equilibrium. Gas throughout the canister has had enough time to interact to dissipate inhomogeneities and anisotropies. The situation is quite different in the Big Bang model without an inflation, because gravitational expansion does not give the early universe enough time to equilibrate. In a Big Bang with only the matter and radiation known in the Standard Model, two widely separated regions of the observable universe cannot have equilibrated because they move apart from each other faster than the speed of light and thus have never come into causal contact. In the early universe, it was not possible to send a light signal between the two regions. Because they have had no interaction, it is difficult to explain why they have the same temperature. Historically, proposed solutions included the Phoenix universe of Georges Lemaitre, the related oscillatory universe of Richard Chase Tolman, and the Mixmaster universe of Charles Misner. Lemaitre and Tolman proposed that a universe undergoing a number of cycles of contraction and expansion could come into thermal equilibrium. Their models failed, however, because of the build-up of entropy over several cycles. Misner made the conjecture that the Mixmaster mechanism, which made the universe more chaotic, could lead to statistical homogeneity and isotropy. Flatness problem. The flatness problem is sometimes called one of the Dicker coincidences. It became known in the 1960s that the density of matter in the universe was comparable to the critical density necessary for a flat universe. Therefore, regardless of the shape of the universe, the contribution of spatial curvature to the expansion of the universe could not be much greater than the contribution of matter. But as the universe expands, the curvature redshifts away more slowly than matter and radiation. Extrapolated into the past, this presents a fine-tuning problem because the contribution of curvature to the universe must be exponentially small. This problem is exacerbated by recent observations of the cosmic microwave background that have demonstrated that the universe is flat to within a few percent. Magnetic monopole problem. The magnetic monopole problem, sometimes called the exotic relics problem, says that if the early universe were very hot, a large number of very heavy, stable magnetic monopoles would have been produced. This is a problem with grand unified theories, which propose that at high temperatures the electromagnetic force, strong and weak nuclear forces are not actually fundamental forces but arise due to spontaneous symmetry breaking from a single gauge theory. These theories predict a number of heavy, stable particles that have not been observed in nature. The most notorious is the magnetic monopole, a kind of stable, heavy charge of magnetic field. Monopoles are predicted to be copiously produced following grand unified theories at high temperature, and they should have persisted to the present day, to such an extent that they would become the primary constituent of the universe. Not only is that not the case, but all searches for them have failed, placing stringent limits on the density of relic magnetic monopoles in the universe. A period of inflation that occurs below the temperature where magnetic monopoles can be produced would offer a possible resolution of this problem. Monopoles would be separated from each other as the universe around them expands, potentially lowering their observed density by many orders of magnitude. Though, as cosmologist Martin Rees has written, skeptics about exotic physics might not be hugely impressed by a theoretical argument to explain the absence of particles that are themselves only hypothetical.